this second to last section in anatomy that we're going to go through is on the anatomy of the ear and how the ear works for hearing, and that's physiology of hearing. So let's start with the outer ear. Part of the outer ear is this cartilaginous structure on the side of your head. This is referred to as the pinna or as the auricle. And the function of the auricle is that it helps capture and funnel sound down into your ear canal. And when we say sound, what I'm talking about is waves of compression and rarefaction, meaning vibrations. Waves of vibration that move through the air, get captured by the auricle and funneled down into what is known as your ear canal, or the external auditory meatus is another word for it. Meatus. You're going to see that word here somewhere in a minute. And the ear canal has a couple of different functions. First of all, it transmits the sound, the vibrations that are moving through the air that have been captured by the auricle. It transmits those vibrations down to your eardrum. The ear canal also has a protective function. The inside of the ear canal is ciliated tissue. So if you remember, we discussed ciliated epithelial tissue when we talked about the respiratory tract. And this is tissue where the superficial cells have these little flagella that wave like this. And so any particulates that get into your ear canal, the ciliated tissue of your ear canal is waving out, trying to pass that particulate from one to the other, like that, trying to clear the ear canal of any foreign matter, of any foreign particulates. Another level of protection is that the tissue on the inside of your ear canal produces earwax. Another word for earwax is cerumen. So you have the cerumen being produced in the ear, and this is that yellow sticky stuff. So any foreign material that happens to float into the ear is going to get stuck on that cerumen. And there comes a point where it becomes such a mass that it's either going to fall out, or maybe the ciliated tissue of your ear canal is going to help pass that cerumen with the particulate matter out of your ear. So that's the outer ear. The outer ear is the auricle and the ear canal, also known as the external auditory meatus. The purpose of the outer ear for hearing is to gather acoustic energy, meaning vibrations moving through the air, and to direct those vibrations into the external auditory meatus, into the ear canal, to pass down to what is your eardrum, also known as your tympanic membrane. All right, so if the purpose of the outer ear is to receive and direct acoustic energy down to the eardrum, it's the purpose of the middle ear to take that, to receive that acoustic energy and change it into mechanical energy, meaning this energy is going to go from waves, movement of molecules in the air, compression and rarefaction of molecules in the air, into actually moving the tympanic membrane, which is your eardrum, which is going to move the structures of the middle ear. So the middle ear is all about converting acoustic energy into actual movement of the body, mechanical energy. What sound wave is? So when I clap my hand, when my hands come together and get really close and smack together, what they have done is they have crunched together all the molecules of air around my hand. And then those molecules of air that have been squinched together, they're going to move this way and push another molecule of air, and then they're going to come back. But that molecule of air that they just pushed, he's going to move as well, and he's going to push the next molecule of air, and he's going to come back. And then the next molecule of air is going to push the next molecule of air. And that is going to happen until this wave of energy that I've created at my hand reaches the molecules of air that are up against your tympanic membrane. And those molecules of air up against your tympanic membrane then are going to be pushed by that same wave. But they're not sitting against air, they're sitting against the tympanic membrane. So now they're going to be pushing on the tympanic membrane, and then they're going to move back to where they were, and they're going to pull the tympanic membrane with them. So when you think about sound waves, and I talk about molecules of air pushing one another, I'm not talking about I'm clapping my hand and molecules of air are shooting from my hand through the air and hitting your tympanic membrane. That's not what I'm talking about. I'm talking about one molecule of air pushing another, pushing another, pushing another. How I do this when I teach this class live is I have like 15 students get up to the front of the class and line up. And the first student, I say, you're the place where the sound is coming from. You're the hand clapping or you're the vocal folds. And then the other student on the end, I say, you are the tympanic membrane. And all the students in between that are shoulder to shoulder, I say, you are the molecules of air between the sound source, meaning my hand clapping or the vocal folds or whatever it is, and this guy on the end, which is the tympanic membrane. And then I come around to the guy on the end that is the sound source, and I push them really hard. And everyone in that line does this. And you see this wave of compression move through the people until that person on the very end, that is the tympanic membrane, he gets pushed. And then everyone straightens back up and they're in the same order. That's what that is what a sound wave is. It's not that I pushed one guy and he ran all the way across the room and pushed the tympanic membrane guy and then came back. It's the difference between if you're standing in the surf and the waves are gently coming in and you feel that back and forth. It's the difference between that happening to you and someone spraying you with a water hose. These are two totally different things. So that is how the movement, the compression and rarefaction, that is the squishing together of molecules and then the pulling and then them being pulled apart after they've been squished together. It is a wave that you're creating in the molecules of air that moves through the molecules until that wave gets to the air, the molecules of air against your tympanic membrane and moves your tympanic membrane. So you've gone from an acoustic energy, meaning energy just traveling through the air, to the actual movement of a body part, meaning your eardrum, your tympanic membrane. All right, so let's get a little bit more in depth in talking about the tympanic membrane and the middle ear. So your eardrum, your tympanic membrane, it is a little very thin piece of tissue that seals off your middle ear from your outer ear. And really the only thing I want you to carry with you about the tympanic membrane is, as a speech therapist, if I take an otoscope, which is that little light thing that doctors use to look in your ear, if I take an otoscope, if I'm looking in a child's ear or an adult's ear, I don't know too much about what I'm looking at because I'm not an audiologist, I'm not a medical doctor. When I'm looking in the ear, I'm not looking for that many things. If it's a child, I'm looking in their ear just to see if there's like something in there, like a Lego or something. I'm looking in there to see if I can see this thing right here. You see that? That is known as the cone of light. So I know enough to know that when I am looking at the tympanic membrane and there's a light shining, the otoscope shines a light down there on the tympanic membrane, I should see this image right here, this reflection. That's known as the cone of light. What the cone of light tells me is that the tympanic membrane is in the correct shape that it's supposed to be, meaning there's no pressure on the inside of the middle ear that's pushing out on it. If there is pressure in the middle ear that is pushing out on the tympanic membrane, you're not going to see the cone of light. And if you don't see the cone of light, then in your thinking there's pressure within the middle ear, then middle ear infection is usually going to be the cause of that pressure. And what we're talking about is fluid in the middle ear. And that can be a problem for children because that means they're not hearing speech very well and they won't develop their speech very well if they can't hear the speech of others. All right, so now we have made it behind the tympanic membrane. And there is a series of 3 bones that stretches through the middle ear that connects the tympanic membrane to your primary structure of hearing, which is the cochlea. The first of these bones within the ossicular chain is known as the malleus. The malleus is connected to the tympanic membrane. So let me draw real quick. So here's the malleus. So the tympanic membrane would be like here, right? So the ear canal would be like this. So tympanic membrane. So behind the malleus, you have the incus, and behind the incus, connected to the incus, you have the stapes. So these 3 bones form a chain that connect the tympanic membrane with, and I'm just going to draw a very poor illustration here of the cochlea, okay? Now that is an extremely tiny cochlea, don't take that literally. So you have vibrations moving through the air that are captured by the auricle, funneled down into the ear canal, down to the tympanic membrane. So this is waves of vibration moving through the molecules of air through the ear canal until that wave of push and pull gets to that wave of compression and refraction, which is like the push and the pull that I discussed when I was mentioning all the students lined up side by side. Eventually that reaches the molecules of air up against your tympanic membrane, and then those molecules of air push and pull on your tympanic membrane. And if the malleus is connected to the tympanic membrane, then when the tympanic membrane moves back and forth, the malleus is pulled and pushed, and the malleus is connected to the incus, and the incus is connected to the stapes, and the stapes is connected to the cochlea. And when the stapes is pushed and pulled, it moves in and out of the cochlea, creating waves in the fluid of the cochlea. And we're going to get to what that means in a minute. So here you see a better illustration. So sound wave comes down, pushes and pulls on the tympanic membrane, which moves the ossicular chain, which pushes the stapes in and out on the cochlea. So what you have is the outer ear has gathered acoustic energy. The middle ear has taken that acoustic energy and has turned it into mechanical energy, meaning you have the tympanic membrane and the ossicular chain actually moving, and the stapes is pushing and pulling on the cochlea. So the ossicular chain is delivering now that mechanical energy to the cochlea. So the ossicular chain, the tympanic membrane and the ossicular chain, the middle ear, has a special job to do. It has to deliver enough energy, enough push and pull to the cochlea to stimulate your hearing. And it turns out that it requires a good bit of mechanical energy to be delivered to the cochlea to stimulate your hearing, for you to be able to hear. So the ossicular chain has a mechanism in which to do this, in that it collects a small amount of energy, which is sound waves, and it collects sound waves, which is a small amount of energy, but it collects it over a large surface area, relatively large surface area, which is your tympanic membrane. So there's a little bit of movement of a large surface area, which is the tympanic membrane. And if you look at this image here, you can see that all the energy from this structure right here, the tympanic membrane, which is a larger structure, is concentrated into a much smaller surface area, which is the foot plate of the stapes right there. And the foot plate of the stapes pushes and pulls on an opening to the cochlea that is known as the oval window. And we're going to get to the oval window here in a minute. But let me show you the surface area of the eardrum. You look at it like this. Compared to that little tiny space that the stapes is pushing in on the oval window, which would be about like that in relation, you can see that the surface area of the tympanic membrane is huge. The surface area that is being pushed and pulled on by the foot plate of the stapes on through the oval window of the cochlea to stimulate your hearing is much smaller. So what we're talking about is that the tympanic membrane and the ossicular chain gathers a small amount of energy over a large surface area, but focuses that energy into a much smaller surface area, so it's delivered with much more power. So An example is that if I have my hand and I do this, okay, I'm taking that amount of energy and I'm spreading it over the surface area of my hand. That doesn't hurt, right? But if I took that same amount of energy and I focused it into a much smaller surface area, like a point. So let's say I had like a knife strapped to my hand and I did this. Same level of force, but focused on a much more smaller surface area, that tip is going to do far more damage to my body. That's what we're talking about here. Small amount of force over a large surface area, but focused down more to a point so that the stapes is able to deliver enough push and pull to the oval window of the cochlea to stimulate hearing within the cochlea. And we've already mentioned the Eustachian tube a little bit, but here's a great illustration that shows you where it is. It opens into the nasopharynx and it runs up into the middle ear, runs up to the middle ear. So this is the tube that connects your middle ear to your nasopharynx. So understand that that is the only point of connection between your middle ear and the outside world. Here it is right here. So that is the only way for fresh air to get into the middle ear. So the Eustachian tube allows the middle ear, which is otherwise sealed off from the outside world, to receive fresh air. So the Eustachian tube allows the middle ear to be aerated. And recall that it is the tensor veli palatini in your nasopharynx that dilates the nasopharynx end of the Eustachian tube, opening that Eustachian tube. So when you pop your ears like that, when you yawn and you hear that pop, what you're hearing is the Eustachian tubes dilating and the air within your middle ear connecting to the air in the environment.